let's make a cyanohydrin. That's the nucleophilic addition of H and CN across a double bond. So here's our cyanohydrin. Here's our carbonyl. Right, we added an H to make it into an alcohol, and the CN was attached. So cyanide, the CN minus ion, is a very powerful nucleophile. So the carbonyl does not need to be activated. Right, it does not need to be protonated. It's a negative nucleophile. It just straight out attacks that carbon, kicks the electrons up to give us this tetrahedral alkoxide intermediate, which is then protonated by an HCN. So we need to have some of both. We need to have HCN and some CN minus present. So here is HCN. That protonates our alkoxide, regenerates CN minus, which can be used as a catalyst. So if I have a large amount of HCN with just a tiny amount, catalytic amount of sodium cyanide that we've also added, okay? Be careful with sodium cyanide. Tiny little bit, milligrams of that can kill the person. It turns out it has to be this way because HCN is not a strong enough acid to protonate the carbonyl oxygen. Okay? We do need a fairly strong acid. Okay? We need some form of actual real hydronium present in the solution. So, HCl, H2SO4, something like that. Actual decent acid. HCN's pKa, I don't remember, 8, 9, 10, something like that. It's not as strong as the actual quote-unquote strong acids like we talk about. So we have to have a little bit of this negative nucleophile there because there's no way for us to protonate that carbonyl oxygen to begin with. We'll see later in our amine chapter especially how cyanohydrins can be useful synthetically. If I have a cyanohydrin, I can reduce it with lithium aluminum hydride with LAH, pretty much adding hydrogens all across that triple bond there. So to make a CH2NH2, where there was a C triple bond N. So here we've got an alpha hydroxyamine, which is a very important synthetically useful compound for pharmaceuticals and things like that. Nitriles can be hydrolyzed to make carboxylic acid. Okay, we'll talk about that later though.